In order to solve the governing equations, we're going to need some additional information about the problem that will take the form of boundary conditions. We'll recognize three types of boundary conditions, and they're conveniently called type 1, type 2, and type 3. There are some other names where these boundary conditions are named after people. Type 1 is a Dirichlet, type 2 is Newman, and type 3 is Cauchy. And these are equations that apply on the boundary of a domain. So if our problem domain looks like this, then the governing equations are applying here within the domain, and boundary conditions, these type 1, type 2, or type 3 conditions, apply on this outer edge here. So the first one, type 1, a Dirichlet condition, we're going to specify C, the dependent variable on the boundary. So we would say, okay, I know what the dependent variable is here, and I'm going to specify. So there's an equation that would be C equals, let's call it C1, where C1 is a could be a function, could be some distribution over the boundary, could vary with time, but it's something that we know. Another possibility is that we specify the gradient of the dependent variable, shown right there, on the boundary. And typically what we'll do is specify the gradient normal to the boundary. So n is the normal vector, so it's going to be a vector that is perpendicular to the boundary, like this. And this del C is the gradient of C, and this dot product takes the component of the gradient that is normal to the boundary. And here we specify that we know it, and it's equal to C1. Now another version of this is, instead of using the gradient of C, we use the flux. And the flux is often proportional to the gradient. And so this will serve as another version of the type 2 boundary. A common one is to say that the flux normal to the boundary is equal to 0. This would be a no flow, or we're saying nothing is crossing the boundary, and that's what's written here. And then the type 3 boundary, this is called the Cauchy condition, and we say that the flux normal to the boundary is proportional to the value of the dependent variable at the boundary. And here we have two constants that we can also use to specify various aspects of the condition. Okay, so this will give us a little more flexibility, and we'll be talking about all of these boundary conditions in more detail later.